If ever there was a symbol that says loudly, "Do not put this in your pants," this is the symbol. Anytime you see this, we're talking about something that is really odd called nuclear chemistry, and I really have trouble calling this chemistry at all, only because it is so weird. And what I mean by that is that everything else that we've talked about thus far having to do with the way that chemistry works has everything to do with those outermost subatomic particles called electrons. They're the things that are getting shared or stolen or being lost. That really describes the majority of the reactions that are happening in our bodies, around us on an everyday basis. It turns out that all of that kind of stuff, that's always from kind of the outside of an atom. And what we're going to be talking about here with nuclear chemistry is that this thing, this little tiny thing that we talked about, I think, in the first week when we were talking about atomic structure called the nucleus, is actually going to undergo changes. And this is a really odd phenomenon that really wasn't even understood until the early 1900s. So be aware that nuclear chemistry is a really different kind of thing, and I'm never sure where to fit this into a chemistry class because it is so much different than everything that we've talked about up to this point, because it involves changes to the nucleus. And keep in mind, when you change the nucleus, you have a very serious possibility of actually changing the identity of your elements. Turns out that's exactly what happens in nuclear chemistry. It wasn't something that people expected, certainly. In fact, the kind of beginnings of chemistry were with the alchemists, and they were kind of poo-pooed for the longest time because they were constantly trying to turn turn lead into gold. And, for hundreds of years of the initial part of the formation of chemistry is we were kind of working against the alchemists to try to say, no, they were crazy, they didn't know what the heck was going on. Even though they were completely incorrect in many of the things that they said about that particular subject about turning lead into gold. Turns out the idea of being able to turn one nucleus into another actually is possible. And so that's kind of what we're going to talk about. And it turns out lots of you guys are going to be going into health fields and some other fields that involve a whole bunch of nuclear chemistry because it is so useful. Just by way of a little bit of review, it's probably good to remember that we've symbolized atoms like this in the past, right? This is carbon-12, which is a particular isotope of carbon, and we talked about a couple of different parts here, and this slide will hopefully just kind of remind you of a couple of things, like the symbol of the element. Keep in mind that in the nucleus, we've got protons and neutrons. And keep in mind also that we have this thing called the mass number, right? The carbon-12 of this carbon-12 is the fact that we've got a total number of 12 protons plus neutrons. And also down below there, we also have what's called the atomic number, and that's the 6 right there. And that's the thing that gives the identity to an element, right? If this was a 7, it wouldn't be a carbon. Right? If it was a 5, it wouldn't be a carbon. Carbon has a 6 associated with the 6 protons that have to be in its nucleus. So, we kind of have to review those terms. Also, we have to review this idea that there is such a thing as isotopes, that there are actually possibilities of having different number of neutrons in those atoms. What hopefully we'll recognize today is that number of neutrons actually is really important. It's kind of what I think of as almost like a stabilizing influence, and it turns out that there's a certain number of neutrons for a particular atom that make it not radioactive, and then if you get outside of that kind of range, then you have the possibility of having something which is called radioactive, which we'll define in a second. But just to let you know, there are some nuclei that are always radioactive. It turns out anything on the periodic table of an atomic number 84 and above actually has to be radioactive. In other words, for those particular nuclei, there is no perfect number of neutrons. Every element below that at least has the potential for being radioactive if you don't have that exact right neutron count. So what is radioactivity? It turns out that radioactivity has to do with an unstable nucleus. if it's an unstable nucleus, it's very likely that it's going to decay to some other kind of element or some other kind of nucleus. These things are called radionuclides. They also have a typical decay series. And for a lot of folks, when you say radioactivity, it's something that is just, terror inducing, right? The idea of something being radioactive is really scary for a lot of people. But the funny thing is, it turns out that there's actually radioactivity around us all the time. Obviously, it's not super concentrated. It's not really strong, in other words. But there are radioactive sources all around us. In fact, if we had a Geiger counter and we were in class, I would take it out, and when I held it up to people, it would start to go crazy. And it's actually because there are a certain number of nuclei that are decaying in your very own body. Not very many of them, but they're at least, the machine is at least sensitive enough to kind of pick up some of those things. So this slide gives you kind of an idea of that, is that the U.S. population, and every population for that matter, always has a certain amount of radioactivity around them. You might imagine that, in some sort of like X-ray setting, or, in some sort of lab, you certainly would get some sort of exposure from that. That's kind of one of the reasons that your dental hygienist, leaves the room when he or she takes X-rays of your teeth. It's because she's just trying to minimize exposure to that radiation, because it turns out that the radioactive nuclei release some pretty energetic particles that can actually damage your DNA and mutate cells and stuff like that. So you really want to minimize this stuff. Out here, I guess there are some communities that have problems with radon, but I remember that I used to play hockey all the time in the basement, just like floor hockey, because I obviously didn't have a rink in my basement. It came out several years after, I had left my house, that we had these horrible radon sinks in the basement. It's this really heavy gas that isn't the most healthy thing. So, look at me. I've been exposed to radon my whole life, and look at me. I'm perfect. But anyway, another word for this is called transmutation, this idea that you can actually have one element that either by natural or artificial means becomes something else. I should mention, I hope to post a couple of resource guides. Make sure you check those, because it'll definitely help to organize the droning that I'm about to do at you. There are a few types of radioactive decay that it's important that you recognize. These are all, at least at this point, are all going to be kind of non-man-made decays. These are just kind of things that naturally happen when a nucleus is unstable and hence radioactive. So a couple of different examples. One is alpha decay. This is something called an alpha particle, and so we're kind of in the realm of the small once again. And there's all kinds of really bizarre activities that happen at a really, really, really small atomic scale. Turns out you can actually lose the equivalent of a helium nucleus from an atom. This is something that's really common to something like uranium-238. An interesting thing about uranium-238, it's actually the heaviest element that is natural, and it's actually from exploding, giant explosions of stars. So it's kind of present in an ore. It's really yellow, and if we were in class, I'd show you a little bit. It's mildly radioactive. It produces a proton out of its nucleus, right? And so one of the things you'll kind of notice here is that conservation of mass that we've talked about before is kind of an easy way to figure out what's been lost from a nucleus. So for instance, if we know that this alpha particle, which by the way is often just symbolized with a Greek A, which is kind of a fancy looking fish A, you'll notice that all of the mass numbers have to add up on both sides, right? So here you'll notice 234 plus 4 does in fact equal 238. And then also you can do the same thing with atomic numbers. If, for instance, a really common type of problem is where I don't give you what particle was lost, or ask you to identify what particle was lost, and you can just kind of play this game where you say, well, hey, this must be an alpha particle because we see a 92 here and there's only a 90 here. Right? What's missing? Oh, that must be a 2, right? And so that's kind of a really common use of that. A lot of you folks are going to end up with being an A&P or going into some sort of biological field. So I just kind of included a couple of slides that would talk a little bit about some of the biological effects. Alpha particles, in terms of kind of biological effects, they're pretty slow moving, so they don't really cause much damage unless, of course, you ingest them. And then, the idea is that that skin is kind of a protective layer. And then if you kind of, are dumb enough to ingest something like this, then the alpha particles can really do some real damage. Those of you with a little bit more of a physics bent, they're pretty slow moving. They only go about 1/10 the speed of light, which is still pretty damn fast. Other kinds of particles that you should know about. Another one is called a beta decay. And really what this thing is equivalent to is this like crazy super high energy electron. And so one of the ways you know you're in the bizarro land of nuclear chemistry is that, we talked about the fact that a nucleus only has protons and neutrons. Well, it turns out that atoms can actually kind of spit out electrons. It turns out neutrons are essentially made of kind of one proton and one electron, kind of like, think of it as like congealed together. So it turns out you can actually lose an electron from the nucleus, even though technically there are no electrons in the nucleus. Like I said, the science of small is really bizarro. So here's an example of the loss of a beta particle. Again, you just kind of play that game where you notice that the left side of the world has to equal the right side of the world in terms of mass, right? And so we know that electrons really have no mass, or very little mass compared to the mass of everything else. And then you can kind of see that that -1 plus a 54 does in fact equal 53. Biologically, these things are a little bit more interesting. They travel much faster than those alpha particles, which means that your skin is not enough to protect you, right? And so a lot of the time that you, or if you've ever heard about like serious burns from radioactivity, let's say in Hiroshima or Nagasaki, those two places that had a nuclear bomb dropped on them. This is a source of quite a bit of the major skin burns. And the interesting thing, like I said, from you folks that are going to end up in biology, is there are actually a whole bunch of really useful things that we can do with these things. We can use like certain isotopes, like this yttrium isotope, to kind of hit tumors. Like if you ever hear about somebody with cancer that's undergoing radiation therapy, or if you've ever had an animal that underwent radiation therapy, it's pretty useful. A lot of those things are kind of a directed beta decay to try to, kill the tumor. And again, in class, I'd have examples of all these different things, and we'd actually have a little Geiger counter, and we would have seen that pretty substantially thick lead would be needed in order to like truly stop the little beta particles that we were sensing. Some more kind of wacky stuff that these nuclei can emit. Turns out that there is a version of an electron that has the opposite charge. So we're talking about something that is positively charged, but is just like an electron. Turns out that that can be emitted from the nucleus. And it's called a positron, and the way that you abbreviate it is like that. Oh, I did forget about one thing having to do with beta decay. Keep in mind that it can be symbolized in several different ways. Right? And so the positron emission, you can see that this is how you can recognize it. Once again, you play that kind of left side has to equal the right side kind of thing. Another really common way to ask questions regarding this is for you to identify what, given the fact that something, say, eliminates a positron, what is the nucleus that is produced, right? And so you kind of do the same exact thing, right? If a positron is produced and it has to equal this, you can figure out that boron is in fact what's left over. Biologically, one of the most interesting things that you can do with positron emitters is you can do what's called a PET scan, or positron emission tomography. Some of you might have even known somebody that's had this procedure done or had it done on you. So I just kind of included a couple of links that you can link to in the PowerPoint. And if you don't want to do that, I'll just talk at you about this. The really cool thing is that they inject this little positron emitter. Usually it's like a fluorine nucleus on a sugar. And so what happens is that any kind of sites that are very, very, very active in terms of their sugar metabolism, like let's say a tumor growth or some area that maybe shouldn't be have a bunch of energetic needs. You can actually see it in real time what's happening in the body. So here's an example of a patient with Parkinson's disease. I'm sorry, this is a normal patient, and these little things in the brain are called basal ganglia, and they typically have quite a bit of metabolism associated with them. And then in a disease like Parkinson's disease, you can see like a significant decrease in the activity of those things. That red is kind of became a green color. And then those of you that are like Robin Williams fans or know a lot about kind of medicines and stuff like that, there's something called levodopa that has actually a movie about it. I can't remember what the Robin Williams movie is called, but anyway, it's about these people that were essentially catatonic in like the 1950s and couldn't quite figure out what was going on. They gave them this medication called levodopa. It turns out what they were doing was and those people that were formerly in a catatonic state suddenly became aware, and what was happening is that we were figuring out a way to kind of get their basal ganglia more active. So here's just some of the scans of those individuals, or a similar set of individuals after that. So pretty exciting stuff, and quite honestly, you guys that are heading into the biological field, there's all kinds of different chemistry going on behind it, but it's not always necessary that you kind of understand the ins and the outs of every single little thing that you do in medicine. But it is kind of a good idea to kind of have just a real basic understanding of some of this stuff. In terms of particles that can be emitted, this one is, technically a particle, but it is a really oddball particle. It's essentially just like a little tiny packet of almost pure energy. It's called a gamma particle, and we abbreviate it with this kind of like upside down cursive L. And you notice it has no mass and also no atomic number. And that's because it's essentially pure energy. Now, you might imagine something that's like a little packet of energy is probably going to be super powerful. And so typically this thing is, these things that travel at the speed of light is really severely damaging to tissues, penetrates really, really deep into organ systems. To really block it, you really have to have some thick lead. I don't know if you've ever held a piece of lead in your hands, like a plumb bob you use for like surveying or something like that. But that sucker is heavy. So imagine 5 centimeters, right? So that's like a little under 2 inches of like straight on lead. This is usually why you have to wear, like at the dentist, that big giant iron vest, which makes you feel so powerful, is because you're trying to block out gamma radiation from getting kind of overexposed. This is some pretty serious mamba jamba. Usually gamma particles aren't emitted all by themselves. Usually they're accompanied by the loss of like an alpha particle or a beta particle or something like that. Just kind of other random information that's good to know about nuclear chemistry, especially in like a one day introduction to like a super complex subject. I just kind of threw a couple of things on this slide here. This idea that anything past uranium, right, like 93 and higher, they're all artificial and man-made. And in other words, they even exploding stars aren't massive enough to kind of throw these nuclei together. So it turns out we figured out really good ways, or I should say the physicists have figured out really good ways of kind of smashing things together and developing these artificial man-made elements, which you'll see everything past 92 is actually non-natural and artificial. There are 90 naturally occurring elements. Keep in mind that there are 2 that we had to make among those like first 92 there. So there's actually only 90 that are naturally occurring. Turns out technetium and promethium are also made in the lab, and we could talk about reasons for that if you care, but you don't. And then we also mentioned this, but I just wanted to make sure you remember it, that anything past polonium is radioactive. Polonium itself is radioactive no matter what you do to it, and anything greater than that is also radioactive. And then when you look less than polonium, you at least have the opportunity for radioactivity depending on the number of nuclei that you have in your nucleus. So we already talked about this idea that unstable nucleus or nuclei are said to be radioactive. One other concept that we should at least be familiar with, especially in a health setting, is this idea of half-life. It's probably the best way to show this is with an example. So you've probably heard about, let's say, dating, I don't know, an archaeological site with C14 dating. And so the whole idea of this is based on that nuclear decay happen at like constant rates, right? If you talk about some sort of passive process that is outside of any kind of human intervention, if you have a certain amount of radioactive nuclei taken in a total sample, it'll always have a constant half-life that doesn't seem to vary based on anything that we can discover. And so, for instance, carbon-14, the reason that's used for a lot of archaeological digs and stuff like that, is that it's said to have a half-life of about 5,700 years here. And so the idea is that if this n sub 0 here, that's where the total sample starts. So let's say that you start with 100 grams of material. It turns out you have exactly 50 grams after 5,700 years, or 5,730 years. If you wait another half-life, right, or another 5,730 years, you're going to have half of your half, right? So a quarter amount of your total sample is going to be available here. And this is going to keep going until this thing asymptotically approaches 0, which, by the way, is the reason you can't use like a C14 if you want to figure out how old a rock is, for instance, right? You wouldn't use a C14 because the half-life isn't long enough. You'd use something like, I don't know, uranium-238, which has like something like a 4 billion year half-life that scientists have measured. So what do you need to do? Well, there's a couple of homework problems where you'll have to use this idea of a half-life. And there is an equation that I think your book talks about, but most of the problems that I've assigned, I intended to make kind of whole number intervals, because when it's not just a perfect 1 half-life or 2 half-life or 3 half-life, right? Sometimes the calculations require a little bit more algebra. So most of the problems that I'm going to ask you, if you know the half-life of something, you just kind of construct yourself a little table here. Just remember to start at 0, right? You go through a couple of half-lives, and you just essentially have a column where you just kind of add up the number of years, right? I just kept adding 5,730 to each half-life here. And then each time you have exactly half of the amount that you started with, right? And you can notice that each one of these entries goes down by half. So if you have some question that says, hey, how much is remaining of an original 35 gram sample after 4 half-lives, you construct yourself a little table, and lo and behold, you find out that there's about 2 grams left of C14. So this kind of thing is super useful, especially those of you that are going into any kind of imaging or radio techs or something like that, radiography techs, I should say. You'll definitely want to know about this kind of stuff, because obviously if you're injecting your patient with some sort of radioactive sample, you don't want it to be in there forever. And so usually you choose things with like really short half-lives, and you want to make sure by the time that person comes home that they're not peeing radioactive stuff. No introduction to nuclear chemistry would be complete without at least acknowledging the fact that you can use these things in gigantic nuclear weapons. So keep in mind that the energy in nuclear reactions, right, is a tremendous amount of energy, as you probably expected even before hearing me say such a stupid thing. And so where is all that coming from? Well, it turns out that it has to do with E equals mc squared. So grandma's going to be really impressed with you this week when you tell her what you learned in chemistry class. It turns out that the way that we hold nuclei together is actually taking just a tiny bit of mass and turning it into energy. It turns out a tiny bit of mass corresponds to a huge amount of energy. When you look at E equals mc squared, if you've never kind of heard about what these things represent, m is the mass in kilograms. And c is the speed of light in meters per second, and you square that number. And I don't know if you've ever seen light, but it moves pretty damn fast. So when you square that number, you end up with a huge number for just a teeny tiny little bit of mass, and that corresponds to energy. So that thing that is kind of missing from the mass of the nucleus is called the mass defect. And so what you're doing in this nuclear weapon is you're kind of taking some of that energy that is holding the nucleus together, and you're busting apart and letting it bleed into the surroundings, hence this big giant mushroom cloud. So other stuff we should probably know, up to this point, we have been talking about chemical reactions, like even the hottest ones that we would have done in class, like the thermite reaction, which is, used for like welding underwater, which, is a crazy reaction to watch with your very own eyes. That's just pathetic compared to the amount of energy that happens in any kind of nuclear reaction. The energies we're talking about here are just thousands of times greater. And two things you should know is there's kind of two different ways of liberating that energy. One is nuclear fission, right? Which is something where, you basically take a neutron and you have it impact like a uranium-235 nucleus. And what happens is this crazy process where that neutron busts apart the nucleus, right? And this is artificial, right? This is something that, doesn't just happen naturally. You bust it apart, and what you'll notice is that 3 new neutrons are produced. So the idea is if you have something that's dense enough with uranium-235, that each time one of these neutrons hits a uranium-235, it itself produces 3 more neutrons. And so this is kind of the idea of like, that uncontrolled nuclear process that releases a whole bunch of energy. There is this idea that you have to, in order for this process to kind of be self-sustaining, you actually you only cause a nuclear chain reaction when you have like a very dense sample, right? You have to hit something called the critical mass. So if you've been watching the news and hear about countries that have nuclear ambitions, we're always trying to get them to stop enriching uranium, and that's what they're trying to do. They're trying to get enough uranium-235 that they can kind of sustain this horrible nuclear reaction. Without that, turns out that you just pretty much die out. So that thing is called the critical mass. I'm sorry I'm going so fast here, but it's not something that is anything more than just something you just kind of need to know the existence of. If you imagine a nuclear reactor, right, like a lot of people don't understand this. They kind of see nuclear weapons and they say nuclear weapons bad. That means nuclear reactors must be bad. Well, it turns out they work very differently. What you do in a nuclear reactor is you actually kind of slow down those neutrons so that it's not like this crazy self-sustaining explosion, but instead it's this like thing that you have really tight control over. As long as you're in a society that cares about its citizens, like the United States seems to do a lot better job than, let's say, Russia, you have this kind of design of a nuclear reactor where you have these things called control rods with all kinds of different safety considerations that can kind of go down and up and kind of slow the nuclear reaction. If you wanted to go faster and burn hotter, or I should say you're trying to heat up water to turn it into steam to turn turbines for the generation of electrical power. If you want to slow the reaction down, you drop your control rods. If you want to speed it up, you raise your control rods. And so what happens in places like Chernobyl, where some really nasty stuff happened, was they just didn't have enough safety protocols in order to like have kind of triplicate safety having to do with their control rod drive. So like if you don't have a control rod in there and you can't slow the reaction, that's bad mamba jamba, right? But for the most part, nuclear reactors kind of got a bad rap, in my opinion anyway. There's at least a way that we can do it somewhat safely. Of course, the one thing that is true of the fission nuclear reactors is you still have to kind of get rid of all the nuclear waste afterwards, which could certainly cause a huge problem. So having to do with that, what we try to develop, and this is still an active field of research, is this idea of nuclear fusion, right? And when fusion happens, you're actually, instead of trying to bust nuclei apart, you're actually trying to combine them. And this is the way the sun works. So it does work. The only problem is that the conditions of the sun are pretty hard to generate in a lab. And so we're really trying hard to come up with a way to do some kind of low temperature nuclear fusion. But we haven't quite gotten to the sun yet. But hopefully that will happen someday. And I think with that slide, that's pretty much everything that you need to know about nuclear chemistry. Tried to keep today fairly light. So make sure you take a glance at that celebration of knowledge, and I will talk to you soon.